Well, thank you very much, first of all, for the invitation. I hope the talk indeed will be interesting. Yes, I'll try my best. So I will talk about some questions. Let me write questions of symmetry. Let me put it some kind of in this wake form, questions of symmetry and floating bodies. Okay, so let's get started. We will start with some kind of toy exercise in R3, and then we will go to more difficult questions. So the question is the following. When I'm going to write K, yes, most of the time it's going to be origin symmetric convex body. In Rn, well, n is going to be greater or equal than 3 most of the time. If you want, you can think about n is equal to 2, but this is kind of a special case. You'll see why at the end of the story. So please think about maybe the best case is to think about n is equal to 3. You'll see. So we have an origin symmetric convex body. I will write it like k is minus k. And you are given a direction xi. So xi is always going to be the direction. Let's say we are in the 3-dimensional case. Xi belongs to S2. S2 is the unit sphere in R3. Okay. And so the question is the following. Assume that for any direction xi in the 3-dimensional space, the section k intersection xi of your body, so let me draw the picture. So this is your k, origin symmetric origin is here, this is xi, and you hit it with the section xi perp. Xi perp is the set of all points in R3 that are orthogonal to this vector xi. And you have this section here. This is k intersection xi perp, okay? So assume that for any xi, basically all sections passing through the origin, they have a symmetry of a cube. The section has a symmetry of the square of the cube in general in higher dimensions. So what does it mean? It means that there exists a rotation phi xi by pi over 2 angle. Yes, I will write SO2 psi perp, meaning that I rotate here in the subspace inside perp, okay? Such that if I use this rotation phi xi pi over 2 of the section doesn't care. It's still chi intersection psi perp. Yes. So the question is, does it follow that k is the Euclidean ball? B is always going to be the Euclidean ball. So let me clarify a little bit. There are many shapes that have many 2-dimensional shapes that have the symmetry of the cube. For example, you have a square, is a shape like this. You have a disk, but there are many others. For example, if you take cube, yes, and then you somehow add pieces, yes, somehow to this cube so that the thing is invariant under rotation by pi over 2, so it still has the same symmetry. So you have all kinds of shapes like this, and the question is it possible out of the shapes to make a single body which is not a ball? And the answer is no. So the answer to the question is affirmative, yes, it is a ball, and let me solve it. It's very easy in R3, and this is kind of a warming up thing. Is the question clear? I hope it is.
Yes.
Again, in every subspace, yes, if you look at me, in every subspace, I have my own rotation by pi over 2. In fact, if I have one rotation, I have all 4 of them, and I cut back. Yes. So in every rotation, in every subspace, I have a rotation where my section doesn't care. Yes, and I want to say that the only body that could kind of sustain all of the symmetries is the Euclidean ball. Let's do this. This is not difficult at all. So let's consider the radial function. So the radial function of k. So I will write rho k of theta. Theta is the direction again on the unit sphere. And this is going to be the maximum. In a moment, I'll make a picture. Maximum of lambda positive such that lambda theta belongs to k. Basically, again, this is k. Assume that this is origin symmetric, but this is not necessary. For simplicity, everything is origin symmetric. And I have my direction theta. And I walk till I hit the boundary. And this is my rho k of theta. This is my radial function. So what is the idea behind it? The idea is very easy. So I have my S2. This is my S2. This is my sphere. And for simplicity, I take X. This is the North Pole. Okay. What I claim that if I have my condition, yes, so that every section has a symmetry of a square, then the value of my radial function at X is the same as the value of this function at the point W for any W belonging to S2 intersection X perp. So if I have this W here, but for any W, if I have W here, on all of this, at all of these points on the equator, I have the same value. This is what I claim. And why this is so, this is heuristically obvious. So if you take this X and you take this W, they are orthogonal. So this piece is exactly S2 intersection X perp, yes, this equator. And then if I live in this subspace here, if I live in this subspace, if you want, I can draw, this is my Xi, yes, so this is my Xi perp. If I live in this subspace, of course, I can rotate X into W, and my function doesn't care about rotations in the subspace, yes, because rho k intersection Xi perp at any point, whatever, let me put it X. Yes, this is the same as rho k at X for any X belonging to S2 intersection Xi perp. So if I have this, I have my value at W the same as at X, and then all of the values here, all my function, I mean, on the equator has the same value. So this is exactly what I wrote here. Okay, so the function is constant on the equator, but the point X was arbitrary. So if I take now another point, if I take now point Y, and I can repeat the story, yes, and I can have another equator, yes, this is S2 intersection Y perp. So when I have the same property, rho k at Y, this is the same as rho k at, let's say, alpha, for any alpha belonging to S2 intersection, even let me write it like this, for any, yes, alpha intersection Y perp. Yes. Okay, very good, but two equators intersect, yes, definitely. So I have this the intersection points. Hence what I got, because my function is constant here, and my function is constant here, and the equators intersect, hence the function must have the same value. And I got that rho k of X is rho k of Y for any points xy on the unit sphere. And then I got that my function rho k is identically constant. And this is exactly means that k is the Euclidean body. So this is an exercise. So now let's try to solve the same question in higher dimensions. This is already more difficult. So now I want to assume that n is greater or equal than 4 from now on. And I want to repeat the story. But unfortunately, I don't know how to repeat the previous argument. Okay, let's formulate the question first. I have n greater or equal than 4. And what do I have? I know that for any xi belonging to Sn minus 1, this is again the unit sphere. Now we live in Rn. Yes, and I have my origin symmetric convex body now, k in Rn. Please think about the 4-dimensional case now. And I know that for any xi, k intersection psi perp has a symmetry of a cube. Well, let me write has a cube symmetry. Okay, What does it mean? It means, again, if this guy, let's say this guy, this is R4, and this guy is three-dimensional, so assume that this is your section. Yes, this is your section. K intersection psi pure. This is three-dimensional. What you claim that there are three axes. Somehow you don't see how they're directed. They're pairwise orthogonal. There are three pairwise orthogonal axes. And there is a rotation by pi over 2 about each x. So let's call this U1, this is U2, this is U3. This axis live in Sn minus 1 intersection psi pure. Well, if I'm taking three of them, then let's put this 3 here. Yes. And your section doesn't care about this rotation. So let's write this down. So for any xi belonging to Sn minus 1, in general, there are n minus 1 axes, unit vectors. Those are unit vectors. Yes. In Sn minus 1 intersection psi pure. And there are rotations. Let me write them like this. Phi xi uj pi over 2, j from 1 to n minus 1, such that if I apply this rotation, any of these rotations to my section, then the section doesn't care. So this is the condition. Again, if you are in the four-dimensional case, you have three axes, but you don't see them. They just exist. And about every x, you can rotate your body, your section, and the section doesn't care. So the question is, does it follow that K is the Euclidean group? Okay, this is the question. Is it okay? Yes, this is the same thing. So we can try, of course, to repeat the previous argument, even if you have the dependence, so this U1, etc., UN minus 1 somehow depend on Xi. But even if the dependence is continuous or smooth, I still have no clue how to repeat the previous argument. This is the point. Somehow this is not easy at all. Okay, so what to do in this case? And then Christos Saraglu suggested the following very beautiful idea, in my opinion, how to solve this question in all dimensions. So he says, consider the moments of inertia. In a moment, I'm going to recall everything. Yes? Moments of inertia of these sections. This is the key idea, and we will show that the moments of inertia of all of these sections are constant, independent of anything, and then we'll conclude using harmonic analysis that the body must be the ball. So at the beginning, it will be a little bit of this mechanics, and then will be pure harmonic analysis. Okay, so let's do this carefully. So what is the moment of inertia? So moments of inertia, first of all. Let's define them in general case, not necessarily for central sections of the body, but assume that K is a convex body in Rn. Now, you don't care if it's symmetric or non-symmetric. And then think, please, about h of Xi. This is just some hyperplane. Yes, that intersecting the interior of K. And I want this h of Xi to be orthogonal to the direction Xi. The direction Xi is some direction on the unit sphere. Okay. So let me make a picture. So this is K somehow. I'll make it two-dimensional. This is h of Xi. Okay. H of Xi, this is Xi. So this is the section of yours. This is K intersection h of Xi. So I want to define the moments of inertia of this section of my body. So let's forget for a moment that we have a section. Let's just take any L, n minus 1 dimensional convex body. In Rn. And let's look at the moments of inertia. So what are the moments of inertia? First of all, I need to introduce the center of mass of L. The center of mass of L. You know what? Maybe, again, for simplicity, please think that n is 3. If n is 3, then this guy is 3-dimensional, this guy is 2-dimensional. So I want to define the moments of inertia of the 2-dimensional guy in R3. These moments are going to show me how much my body rotates about certain line passing through the center of mass of the body. So I have this L of mine. This is n-1 dimensional, but I mean 2-dimensional on R3. Yes. And I have the center of mass of this guy. And I have the n-2-dimensional subspace. I find subspace passing through the center of mass of the body. Let me call it pi. Okay. So the dimension of pi is going to be n-2, and pi is going to live, well, heuristically, you're going to live in h of xi. So if I come back to my picture here, so this is C of k intersection h of xi, and I have my pi. Yes. So pi is a subset again of h of xi. But again, if you forget for a moment about the 3-dimensional picture and just think that L is the 2-dimensional body on the plane, and pi is just the line passing through, this is a line, okay? This is a line passing through the center of mass, then the moment of inertia is a very easy thing. So you take any point P belongs to the body, and you drop a perpendicular guy, you drop a leg to pi, and you just measure the distance between an arbitrary point to your line. Pardon me, this is the line. You square the distance and you average over the body. Okay. And then what you do, you claim that this is the moment of inertia of your body L with respect to pi. This is the definition. Okay. So it shows you how much this n-1 dimensional guy, or the 2-dimensional guy in the 3-dimensional space, how much it rotates about CL. So about the line passing through the center of mass. So again, coming back to this picture, so you see you have this section, and I want to take the center of mass of the section, and I want to take the line passing through the center of mass, and I want to see how much my section rotates about this line passing through the center of mass. This is the idea. Okay, so let's just come back to our case. You remember we said that K intersection psi perp, this is going to be our L. By the way, they're all going to pass through the same. Our body was origin symmetric. Yes, K was minus K. So the centers of mass of all of these guys are going to be the origin. So we should not worry about it. And we'll consider all lines passing through the origin that live in the corresponding plane. Okay, very good. So I want to consider the moment of inertia. Let's consider this particular case. So let me write particular case according to Christus. So I have this moment of inertia, K intersection psi perp, and I'm going to take this line passing through the center of mass, through the origin. This is a line. If you are, okay, let me write in quotation mark, a line passing through the origin, okay? Through the origin. This is if I'm in the 3-dimensional case, but of course we are not interested in it. We are interested in 4, but just heuristically to explain the definition. Okay, in general, this is a n-2-dimensional subspace passing through the center of mass and living in the corresponding n-1-dimensional subspace. So let me write like this. Okay, so what I'm trying to say that I can express this thing. I have a square here. You remember I have a square. This is a square. So I want to write it down so that we see that this expression is nothing but the quadratic form. So let's write this down carefully. So again, this is my K intersection psi perp. This is my center of mass of K. I wrote projection. Pardon me. K intersection psi perp. This is the center of mass of K intersection psi pure. This is my section. My body is somewhere here. I don't see it. Yes, and I have this pi passing through the center of mass. And I have also the vector eta. The eta is the unit vector. This is the unit vector. Eta should be orthogonal to pi. And eta should live in psi pure intersection Sn minus 1. So meaning we have just 1 degree of freedom. Pi is n minus 2 dimensional. Psi pure is n minus 1 dimensional. Eta is exactly the, well, up to a psi. It's a unique vector up to a psi. The unique vector up to a psi. Okay, very good. So I can pass to polar coordinates. Let's just use polar coordinates. And this is the moment where I'm going to cheat. Just trust me. Okay, trust me. So if you pass to polar coordinates, I can write my moments of inertia. So AK intersection psi perp of pi. This is the same. I can use the notation AK intersection psi perp of eta. Okay, so this is the same if I pass to polar coordinates. This is 1 over n plus 1. And here I'm going to have Sn minus 1 intersection psi perp. Just trust me, please. This is going to be a little bit of a mess, but not too much. And here I'm going to have eta dot theta squared. And here I'm going to have the radial function of my section to the power n plus 1 of theta d theta. This is what I'm going to have if you pass to polar coordinates. This constant is not important. You see, you don't care about it. But what is important, again, I recall that if you have the subspace, then the radial function for vectors in the subspace, this is the same as the radial function of the body for any theta belonging to Sn minus 1 belonging to the subspace. Yes. So this means that I could safely forget about this intersection. There is no intersection, it's just K, the radial function of K. And we see easily that this is a quadratic form. This is a quadratic form. In the coordinates of eta, in eta 1, eta 2, etc. Yes, eta n minus 1. In the coordinates of eta. If you think that psi perp is the coordinate plane, yes, then this is just, you have the n minus 1 numbers. And if you open parentheses, you have that this is a quadratic form. But what I'm trying to say, of course, we have our invariance. And our quadratic form is an ellipsoid, heuristically. Yes, so our quadratic form is an ellipsoid. So let me cheat a little bit. So our quadratic form, I'll write bad things, but heuristically they are true. Our quadratic form is an ellipsoid. Yes, and our ellipsoid and our quadratic form, our moments of inertia, they are very sensitive to our symmetry. So let me write this down. And our moments of inertia are very sensitive. This is, of course, heuristics, but I hope it's clear, to the symmetries of the section. Meaning that if I come back to the formula I had, yes, if I come back to the formula, let me write it down up to a constant. I had this thing, I had this quadratic part, and I had this power of mine, yes, theta d theta. So I know that here I put the intersection without any trouble. And I also know that if without any trouble, I could put my rotations with respect to axis I don't see without bringing any trouble because my sections are symmetric. And hence, if I play with change of variables, then these guys will go to eta. And basically, I can conclude, I omit the details, but they are kind of heuristically clear. If I play with this a little bit, I know that our ellipsoid, so our ellipsoid is invariant under rotations. Yes, about n minus 1 hidden axis, yes. But then by pi over 2, invariant by pi over 2, yes. But then it means that our ellipsoid is a ball, is a Euclidean ball. And if I come back to my language, if I come back, this means that if I take the moment of inertia, yes, of my section. I could write it with respect to pi, with respect to eta, depending on the language you prefer. I claim that this is identically constant. So far, you should see that this is independent of eta, because the ellipsoid became a ball. But so far, you should not see why this is independent of psi. Later on, we will see that this is also independent of psi. So all of these moments of inertia are constant, independent of anything. Right now, please see that this is independent of eta, again, by this heuristic argument. But psi I'll explain to you slightly later. Some more theorems we need. And this is independent of anything, and hence, harmonic analysis comes into play. So let me show you how harmonic analysis comes into play, but let's first recall what is the spherical Radon transform is. Spherical Radon transform. Yes, so sometimes it is called the Funk transform, but whatever the name we use. So we have this guy, spherical Radon transform. So what is it? So I have a function. This is an even function on the unit sphere, continuous. Yes. This is not an issue here, continuous. And I will write Radon transform, spherical Radon transform of eta in the direction psi. What I'm going to do, I'm going to average my function, the values of my function, over the equator orthogonal to psi. So the picture is like this. This is my Sn minus 1. This is my direction psi. This is my Sn minus 1 intersection psi perp. So I have the values of my function f, and I average them over this equator. This is my spherical Radon transform. Now there is this miracle that is well known in harmonic analysis. If f is even, if Rf is identically constant, then f is identically constant. So this is the miracle. This miracle we are going to use. This is the same thing as to say that if all Fourier coefficients of the given continuous function are zero, then the function is zero. This is the same sort of, if you write it in terms of spherical harmonics. But let's use it as a certain black box. Okay, given, it's known, well-known thing. Okay, if you have this, we are done. Why we are done? Because we have our subspace psi perp. We choose an orthonormal system, an orthonormal basis, U1 of psi, etc. Well, let's write them eta. We agreed on eta. Eta 1 of psi, eta n of psi. We have n vectors in the subspace. Orthonormal basis, let me write basis as a human. Orthonormal basis in psi perp. Yes. And we know that all of our moments of inertia of our section with respect to this j are identically constant for any j, 1, etc., and minus 1. This is what we know. Our moments, they don't care about the direction with respect to which we rotate our section. So if we have, we'll just sum them up. So let's sum them up. J from 1, n minus 1, a k intersection psi perp at the j. Let's recall Pythagorean theorem. Yes, Pythagorean theorem. Pythagorean theorem. What is this? So if I had this any vector theta, you remember in the subspace, and then I just take the scalar product with this vector eta j and I square it. Yes, this is an orthonormal basis. I sum this up over j. Now this is the same as the length of the hypotenuse, theta squared, but this is a unit vector, yes? So this is 1. Meaning that if I sum up my moments, I recall what it was. It was 1 over n plus 1. An integral was here Sn minus 1 intersection psi perp. Here we had this eta j dot theta squared. Here we had this radial function to the power n plus 1 theta d theta. This is what we have. So I have this expression here. This is the same as here. Yes. I want to sum it up, so I plug in the sum here. Well, let me make it red. G from 1 to n minus 1. I put it here. And this means that I sort of basically cancel the sum with the squares, because all of these moments were constant, independent of eta, at least eta j's. So this means that we got 1 over n plus 1 an integral Sn minus 1 intersection psi perp, rho k n plus 1 theta d theta, yes, and we got our spherical Radon transform. So what did we get? What is the moral? The moral is that the spherical Radon transform of the power of the radial function of our body is constant and independent of anything. Yes, we recall that all of our moments were constant. Hence, this constant somehow changed a little bit. I don't care about the value of the constant, as long as it is constant. Yes, and I got the spherical Radon transform of the power. So let's sum up. So summing up, just a second, summing up, yes, for any psi on Sn minus 1, the spherical Radon transform of the power of my radial function is identically constant, maybe different constant, I don't care. Here I forgot 1 over n plus 1 again, I don't care, because I could bring it to the constant. Yes, and by harmonic analysis, I know that rho k to n plus 1 is identically constant. And then from this, rho k is identically constant. And from this, I know that k is the ball. So this is the beautiful idea of Christos-Seragou. But I overview this place where I promised that to show that my moments are independent of psi, of the direction. So let's understand what this condition means. What does it mean to have this constant moment of inertia? And for this, exactly, this is the place where we enter to this realm of floating bodies. Okay, so let me talk again from the beginning about these things. Maybe before I jump into this water, what I want to say is that, of course, you don't necessarily need to require that the symmetry of the sections is a cubic symmetry. You can choose your favorite symmetry and try to play this game. And as long as your group of symmetries is rich enough so it makes a Euclidean ball out of an ellipsoid, then you are good. But if you don't have this condition, then this is much more difficult and mostly open. So I will talk about it a little bit in a moment. But so let's proceed a little bit. So floating bodies, again, I have this guy, I have my body, okay, and I have my h of psi, the hyperplane orthogonal to the direction psi, as I promised. And please think that the body is made out of uniform material, so uniform density. Uniform uniform density, but I want to talk about the Lebesgue measure. So in a moment, I'll give the precise definition in terms of geometry, but now think a little bit of physics. Yeah? So you have some object of uniform density made out of wood, let's say, and h of psi is your water surface, okay? You submerge it into the water. And you're going to look at the notion of floating in equilibrium. So I will say K floats in equilibrium in the orientation psi, okay? Psi is the unit vector. So what does it mean? This means floats in equilibrium. Floats in equilibrium. Okay, what does it mean? It means the following. So I'm going to take the center of mass of the body, C of K. So C of K is the center of mass. Okay, and I'm going to take the center of mass of the underwater part. Let's agree that the subspace below the water is H minus, subspace above the water is H plus. So this is the part below the water. So I'm going to take the center of mass, I'm going to write 6 psi. So 6 psi is going to be the center of mass. Yes. Of the underwater part. So K intersection H minus psi. Okay. What I'm going to, of course, I talked about uniform density and constant density, yes? So this is uniform density. So it means that the volume below the water is fixed. Yes, some delta number. This is the number between 0 and the volume of the body. And please fix it once and forever now. Fix it. During the conversation, any number. For example, half of the volume, or third of the volume, or tenth of the volume, whatever you prefer. So you submerged your body by delta, yes, and you took these 2 points. So strictly speaking, if I write that the body floats in equilibrium in the given orientation, I have to write here at the level delta, okay? When delta is like above. Okay, so I have these 2 points, Ck and C of Xi. Let me make again the same picture again, please. So let's go here. So I have this K, I have this water, H of Xi, I have the center of mass of K, I have the center of mass of the underwater part, and I have my direction Xi, orthogonal to my water. So what I'm going to do, so the piece of this is delta, yes? This piece is K intersection H minus of Xi, okay? This is H minus of Xi. So I'm going to take the line passing through these 2 points. Okay, let me call it L. Okay, this is the line. And I recall now, so now I'm giving you the definition. I say that K floats in equilibrium in the orientation Xi if L, better to write L Xi, is parallel to Xi. Or if you want, if the same thing, if L Xi is orthogonal to the water surface. This is the same thing. Okay, so the picture is like this. So heuristically speaking, here you have the gravity, here you have Archimedes. They should balance each other. If they don't balance, then the body falls down. So the picture should be, if you want to stay in equilibrium, sorry. If you want to stay in equilibrium, so then somehow like this it should be. Yes, this is your water. This is the center of mass somehow. This is the center of mass of the underwater part. And you have the line. And you should have 90 degrees here. Okay. So this is the picture. So then it floats in equilibrium in the orientation Xi. This is Xi. Okay, so this is the definition. So it turns out, I will skip now many details, but just please trust me. It turns out that we can characterize this condition when the body floats in equilibrium in every in the given orientation, but maybe let me give you another definition first. So definition. So we say that K floats in equilibrium in every orientation. So floats in equilibrium in every orientation. Yes. Well, strictly speaking, I have to write at the level delta. Yes, at the level delta. Again, delta is any number between 0 and the volume. You fix this number, and this is independent of the direction. Okay. We say that K floats in equilibrium in every orientation if the line we constructed there is parallel to Xi for any direction. Yes, this is a honest definition. And of course, the question, I mean, the first question that comes after this definition, well, not the first, but let me omit many details. So the question of Ulam was, given delta, yes, if K floats in equilibrium in every orientation, does it follow that K is the Euclidean ball? This is the question. Okay. So it turns out that to answer this question, we have to come back to our moments of inertia. So I'm going to be cheating in a moment. And the reason I'm going to be cheating, because we just don't have time. It's already 40 minutes. I have only 10 minutes left. So how to understand if the given body floats in equilibrium at a certain level, floats in equilibrium in every orientation? Yes. So there is this theorem of of Dupin. Yes, this is an old thing, but let me maybe mention all the people that gave their share to this type of thing. So I have to mention Nin Zhang. Just a second. I'm sorry, it will not be alphabetical because I remember. Then Han Huang. Then it will be Elizabeth Werner. It will be Karsten Schutt. It will be Krista Saraglu. It will be Serежа Miroshnichenko, Miroshnichenko. It will be who else? Dan Florentin, Boaz Slomka. And I probably missed someone, but I apologize. Krista Saraglu is here. Yes, everybody's here. It looks like. So all of these people gave their share to this theorem. So the theorem tells you the following. So K floats in equilibrium in every orientation. I am going to cheat a little bit, but let's assume for simplicity K is minus K, because we don't have time, then I don't cheat at all. If and only if moments of inertia of all of these sections by the water surface with respect to all lines passing through the center of mass are identically constant, and the constant is independent of psi and pi. So this is the condition. But maybe let me elaborate a little bit on this condition. Okay, so let's introduce the notion of the surface of centers. Okay, because I want to explain why those moments are independent of psi. So the surface of centers, what is this? So you have K, you had this H of psi, you had the center of mass 6i, and now you want to change the direction of your normal. So this is psi, now this is kind of eta, and you take different center of mass. And then you take another direction, let's say alpha, and you have different center of mass. And what you want to do, you want to unify all of them into some kind of a set. Okay? This set is exactly the surface of centers. So we'll write S delta of K. This is the surface of centers. This is going to be exactly the union of this point 6i when psi belongs to the unit sphere. So we just take all of the centers of mass of all underwater parts. Okay. It turns out that the condition of floating in equilibrium, I could add here one more if and only if. So K floats in equilibrium in every orientation at the level delta if the moments of inertia of the sections of the body by the water surfaces, all water surfaces, are constant and independent of the water surface and of the direction inside the water surface, and if and only if the surface of centers is the sphere. Okay, this is only if. One can say, in fact, more than that. This is a very beautiful theorem. In fact, there are three theorems here of Dupin, but let me elaborate a little bit. Let me make one more picture, and then it will become clear what I promised. So I have my body. This is the piece of my body. This is my water. Okay, H of psi. This is the intersection of my body with the water. Yes, so this is K intersection H of psi. Okay. Here I have my 6i, the center of mass of the underwater part. And please think that this is the surface of centers, S delta of K. In fact, it is really it's not trivial, but this is not difficult to show that the surface of centers is always the boundary of a strictly convex body. Okay, so just trust me on that. So I have the center of mass of the underwater part, and I also have the center of mass of the section. So the beautiful theorem of Dupin tells you the following. So if you take the direction, if you take your line, assume you're in the three-dimensional case for simplicity. You have your line pi passing through the center of mass of the section, and you have your direction eta that is orthogonal to pi. Yes. And assume that this direction eta you are lucky is principal, okay? Meaning that the Gaussian curvature reaches its maximum or minimum in the tangent plane. Okay. So there is a miracle, another miracle here, that the tangent plane to the surface of centers is parallel to the water surface. And then what happened, the following thing happens. So let me write it down somewhere here. I'll write it in green because this is very important. So what is going to happen is that the radius of curvature of the surface of centers in the direction eta, if the direction is principal, this is exactly 1 over delta. The delta is the volume of the underwater part times the moment of inertia of the section of your body by the water surface with respect to pi, where pi is orthogonal to eta as above. This is the beautiful theory. This is a non-trivial thing. It's a long story, but just trust me. This is a well-known thing. So if you trust me for a moment, then we see why those moments were independent of psi. Because you remember our moments of inertia are constant, independent of the direction if we live inside the subspace. But if we live inside the subspace, if we live inside the subspace here, then the moments with respect to corresponding perpendicular axis, they're constant, independent of the axis. Means that the point on the surface of centers is umbilic. But then this condition, what we have here, this condition means that all points of my surface of centers are umbilic. And this is a well-known exercise in differential geometry. I am here cheating a little bit because in order to speak about umbilic points, I need my surface of centers to be C2. Okay, but you can reach this. Just trust me. This is a minor technical issue. Assume that your bodies are smooth. Okay, then you have C2. Then all points on your surface of centers are umbilic. Hence, it must be the sphere, and you lost your dependence on psi. Because you come back to your moments, you didn't believe that the moments are independent of psi, but now you do, because the moments depend only on the radius of curvature. And the radius of curvature are now constant independent of psi. Hence, all moments are constant independent of psi. Okay, and so I proved you finally the theorem of Saraglu. But now let me formulate two problems, maybe two main problems in the field, if you give me 2 more minutes. And then I will talk about other symmetries again for 1 minute. So what did we have? We had our body K, yes, and we considered the surface of centers, yes, as K. So you have this Cxi, and you unified the centers of mass in all directions, yes. So the first question is, assume delta is fixed, yes. Assume delta is fixed, of course, yes. The volume under the water part, is fixed, delta fixed, independent of anything, okay? Assume that S delta of K is the sphere. Does it follow that K is the ball? Yes, this is the first question. This is open for any delta except half of the volume, okay? So the picture is something like this. I have here something like this. This is US delta of K, okay? The second question is, if you look at the envelope of your water surfaces, now let's assume that delta is not half. For simplicity again, I want to assume that this is not half, and I want to assume that K is origin symmetric. Again, I don't want to enter into technicalities. Then, what I want to say somehow that if I consider the envelope of my water surfaces, let me write the envelope of the water surfaces. This is what people call the floating body. The floating body. I don't want to enter into definition right now. So something like this here. This is my envelope. I change my water surfaces, and they all tangent to my envelope. Okay, somehow, and I always chop off the fixed volume. So the envelope of the water surface is a sphere. Again, this is a sphere. Does it follow that K is the Euclidean ball? Again, so you have 2 questions. Both are open except in the cases I mentioned. And what I want, so this is very interesting. So even if you assume that both questions hold, okay, I don't know how to do it. Even if you assume that you have both conditions, S delta of K is the sphere, and let me call this envelope, how to call the envelope, then let me call it K delta. This is the standard notation. K delta is the sphere, both, okay? Does it follow that K is the ball? I don't know. But already I'm out of time. Let me just finish with 1 second. Okay, I didn't have time, unfortunately, to speak about symmetry questions. If you're interested, you can ask me and I will talk about it. But what I'm trying to say that recently we were able to prove, so this all joint results, I forgot to say, but all of this I was talking about joint results with Maria Alfonseca, and then Vlad Yaskin, and Alina Stanku. And recently we with a lot of sweat and blood, we had the following. Yes, so if K is a body of revolution, yes, some ridiculous thing, yes, if K is the body of revolution in R4, only the 4-dimensional case. Yes, and you have these two conditions, both the floating body is the sphere and the surface of centers is the sphere. Yes, then the answer is yes, then K is the ball. But the solution is very long and technical, and I wouldn't be able even to present it in 50 minutes, I'm afraid. So let me stop here. Yeah, this is all I know about this. Yeah, thank you very much.
Okay, thank you very much for a very beautiful talk. Are there any questions or comments?
People keep silence. Huh? Pasha, ask something, no?
Pada has left. So maybe I can ask some questions.
Yes, yes, please. Yes.
So when we have this constant that is independent of the direction, do we know explicitly how this constant look like? I mean, the dependence on K and the delta?
No, I don't know. This is a good question. So the next step would be, if you somehow try to normalize this constant, can you some kind of additional condition, the constant depend, like this constant, for example, the same constant as for the Euclidean ball? Yes, this is a very good question. And then some things we know, some things we don't. So Vlad Yaskin, yes, this is a long story, unfortunately. Yes, so but it's one has to talk. So Vlad Yaskin proved the following. So if you let me tell you, this is a beautiful thing. So you have your K.
Yes.
And you have your floating body K delta. This is your floating body. Yes? And just some coincidence, this floating body is the ball. Okay, some ball, let's say, of radius T. Okay, centered at the origin. Doesn't matter. Everything is invariant in the translations. Yes. So, and then of course, there exists, this is your question. Of course, there exists a ball of some radius R centered at the origin. So that if you take the same delta, you will take the same delta, yes? And if you take the floating body for this ball, will be exactly this guy T. Of course it exists, yes? Of course it exists, because everything is symmetric. You put this is your BT, yes, and just put this R somehow in a smart way so that you chop off delta, yes? Well, clear, it exists. So, but then now I'm coming to your question exactly. What says if by luck, yes, the floating body, so the volume of this large guy is the same as the volume of your body, some kind of normalization thing. This is exactly what you're asking. Yes, then true. Then K is the ball. This is a very beautiful and elegant application of, it's a not trivial thing. It's like a 2 pages proof. It's a very beautiful, elegant application of Jensen inequality. But this is, you see, but for example, if you ask me an analogous question about the surface of centers, I don't know. Or if you ask me kind of the same type of argument when you are trying to align the radii of the floating body and the and the radii of the surface of centers to align them in such a way that they correspond to the ball. The same type of your question, yes? I don't know either.
Yeah. Thank you very much.
Yes,
Yeah.
so this.
So usually we take an arbitrary volume K, and with delta being fixed.
Yes, delta being fixed. Yes.
Yes. So what if we take the quotient of delta and the volume K being fixed? Always fix a portion that is underwater.
No. But this is fixed. The quotient is fixed. This is the whole point. I think that the volume of the body is 1.
Yes.
Okay, and delta is fixed also. Delta is, I don't know, 1/3.
Okay.
You see, and you try to do the story. So this is even if you try to vary delta, this is very interesting. Even if you vary delta, you have the delta in some kind of a neighborhood. Then again, for floating body, if K is origin symmetric, one can show this. This is some kind of an argument of Larman and Barker. Long story. But for the surface of centers, I don't know the question. I don't know the answer. Even if you vary delta. Probably it's not difficult. I don't know if you vary delta, but I don't see how to do it.
Okay, thank you.
Pleasure.
Are there any other questions or comments?
I have a small question. So in the last theorem you have mentioned with 4 authors, is dimension any number or dimension equal to
dimension
4?
any dimension n. What I mentioned with so here 2 things, Pasha.
Yeah,
2 things.
here.
First of all, here, if you have a body of revolution, here delta is anything. Okay, here delta is anything, but not half. Okay, delta is not half of the volume because then the floating body is the point. It's not interesting. You see? So if delta is anything, yes, then this is true for bodies of revolution. This is the whole story, yes? Now, what Vlad did is also for any delta. So here, if you are talking any dimension on any delta, yes? If you are talking about this normalization constant thing, it's also in any dimension on any delta, but 1/2. 1/2 is not interesting, yes? Again, but I mean, of course, if you see, if you take n is equal to 2, I'm of course talking about n greater or equal than 3. If n is equal to 2, then both questions, I mean, it's a long story to enter, but this question is known. This is for any delta, and this question is kind of something is known, okay? Let me tell you, not everything. I mean, some things are known. Yes, some things is known. Some things are known. Okay. I just don't want to enter. It will be half an hour. Auerbach proved the first. He was the first. I have to mention his name always. Auerbach. He constructed a counterexample for half, and then the business started developing, but not much is known. Okay, I just I don't want to enter into this, but briefly like this.
Okay. Maybe next time you'll tell me in details.
Yes. Thank you.
Any other questions or comments?
Can I ask one question, please?
Sure.
Yes.
Hi, I have just general question. You use this harmonic analysis tool, like this spherical radon transform. So why is it so powerful? I mean, what drives if the proof of the does not follow the same procedure as you did in a 3-dimensional case? So
yes. Let me tell you. This is a very good question you asked. So first of all, Saraglu and Miroshnichenko, I gave you the proof using harmonic analysis because I wanted to suppress the time of the talk. You see, usually in 50 minutes, if you want to prove it rigorously, you will not have time. So I wanted to kind of cheat and give an easy proof. So this is why I went to harmonic analysis. This is a kind of dishonest answer to your question. But Saraglu and Miroshnichenko, let me write. Yes, this is a Saraglu and Miroshnichenko, when they considered this question about symmetries of the cube, yes, they gave a different proof. They used, there is a perimetric inequality proof, And I believe that their proof has more future than the one I gave you today. But again, it's a question. So you see, if you have an origin symmetric convex body, and if you want to ask any simple question about sections passing through the origin, then somehow this is very funny. If you don't have harmonic analysis, you don't know anything. And if you do have harmonic analysis, you know everything. This is heuristically, okay? So all objects you meet here, if you have origin symmetric bodies, and you consider certain questions about symmetries, questions of uniqueness, like, for example, I considered today. Yes, if you have this type of a question, your object is a convolution. And the convolution is a very convenient object in harmonic analysis. So if you have it, you will solve the problem. So in fact, answering your question, Saraglu and Meshnichenko, in fact, gave the only instance where I met in my entire life where they avoided harmonic analysis for sections passing through the fixed point. But again, they still used a lot of symmetry, and it is not clear how to move the argument for sections that are not passing through the fixed point. Did I answer your question, Alexander?
Well, partially. I just wanted to ask, like, what is the intuition? Why this harmonic analysis trick is like magical? Why?
Well, I don't know the answer to this question. For me, it's like this. I take it as a black box. If you have a convolution, you have a convolution, you solve the question. You don't have a convolution, you don't solve the question. So, for example, let me give you an instance answering precisely your question. You have the following condition. You have the following question. K is minus K, origin symmetric convex body, for example, in R3. Okay? Alexander, are you with me?
Yeah, I'm following.
Yes. So K is minus K. You know that for any psi, for any direction psi, the sections of your body passing through the origin, yes, this is K intersection psi, they all have the same area. Okay? All have constant area. Okay, does it follow that K is the ball? This is very, very easy question, yes?
So yeah, I read about it, yeah.
Yes, the only solution I know is using harmonic analysis. I don't know any other solution. Now, answering the question, change a little bit if you want to avoid harmonic analysis. Instead of area, put perimeter. Perimeter, I don't know how to write perimeter, just a second, I will write it. Perimeter. Open. So if all perimeters of all central sections of the origin symmetric convex body are constant, show that the body is the ball. It's open.
In which dimensions? In all or?
In all dimensions starting from 3. In all dimensions starting from 3, yes? So this is answering your question about harmonic analysis. Somehow you take it as a prayer, you accept it or you don't accept it, yes? So, but there is no other proof. This is the funny thing, yes? So maybe it's not relevant at all, but somehow it's very handy here, because when you write it analytically, you see there is this spherical radon transform is a convolution with a delta measure, and it's very convenient to work with using spherical harmonics.
Okay, thank you very much for the answer.
Pleasure.
Okay. Any other questions on non-harmonic analysis solutions? Okay, if not, then maybe let's stop today and continue the seminar in the next week. Okay, thank you very much again for a very beautiful talk.
Thank you. Bye-bye.